I'm now going to finish off the proof of Roth's theorem. So there's nothing much more to say because I'm in the middle of a proof. So I'm going to go straight to sharing the screen, and I'll just have a quick reminder of where we've got to so far. So Roth's theorem, remember, says that for every delta greater than 0, there exists an n such that for all subsets of 1 to n, if A has size at least delta n, then A contains some arithmetic progression of length 3. And what we've done so far is to show that as long as n is sufficiently large, so maybe I'll just try to remember exactly what the statement was. So if n is greater than or equal to 2 over alpha, beta, gamma, and I'll say what alpha, beta, and gamma are. I'm not going to write this absolutely properly, but the maximum non-zero Fourier coefficient of A is less than or equal to alpha, beta to the half, gamma to the half over 2, then A cross B cross C. So alpha is the density of A, beta is the density of B, gamma is the density of C, contains some non-trivial x plus d, x plus 2d. Where by non-trivial I mean that d doesn't equal 0. Although actually, as I commented last time, it's not completely trivial even if d does equal 0 if you've got a cross b cross c, but it is trivial if a equals b equals c, which is not quite the case that we're interested in, but it's close to the case we're interested in. And then we also proved that, so that was sort of lemma, I'll call it lemma 1, although I didn't call it lemma 1 in the previous video. And then lemma 2 was for every theta in the reals, and for all epsilon greater than 0, and for all n, there is a partition of 1 up to n into arithmetic progressions p1 up to pm of size greater than or equal to epsilon n over 32 pi to the half, such that the function e of theta x is roughly constant on each pi. And the way I expressed that was e of theta pi has diameter less than or equal to epsilon. So let's say for all I. So that's just another way of saying that this function e of theta x oscillates by at most epsilon inside any of those arithmetic progressions pi. And so now, armed with those two, we're going to prove lemma 3. Actually, we're not really going to use lemma 1, but we'll combine lemma 3 with lemma 1 later on. So let, I think I don't need n to be odd for this, although I do in general wanted it to be odd, so I needed it to be odd for lemma 1. So let A in Zn and be a set of density alpha. No, I'll call it delta. Set of density delta. And suppose that there exists some R. So just recall that this result here tells us that if all the non-trivial Fourier coefficients are small, then we get an arithmetic progression. So that means that we're interested in the case where that doesn't hold, where there is some large one. So this is the hypothesis we're going to have for lemma 3. Suppose that there exists R such that A hat R is greater than or equal to eta. So eta is some other constant. But if I be really formal, I would say let delta and eta be greater than 0 or something. Then there is a progression P of length at least eta n over 64 pi to the half. So that just comes from setting epsilon to be eta over 2 in this bound here, such that the intersection of A with P is a bit denser than A was inside Zn, so delta plus eta over 2 times the size of P. And I just want to stress that this arithmetic progression P is not just an arithmetic progression mod n. In fact, if that's all we wanted, we could get a bound here that's linear in n rather than square root. But we really want it to be something that when you regard Zn as just the integers from 0 to n minus 1 or 1 to n, whichever you prefer, we still have a genuine arithmetic progression, not something that sort of jumps round from n back to 0 or n minus 1 back to 0. So let's prove this lemma, which is not too bad. In fact, what I've got here is a slightly slick argument, but the basic idea is not that hard. So what we shall do is the following. So we'll let R be such that this is the case. First of all, actually, a very important step. Doesn't look important, but it turns out to be really make things a lot easier. Let fx equal ax minus delta for each x. And we make the following observation, then f hat of 0 is a hat of 0, which is just the density of A, and minus delta times just minus delta. Because if you work out the Fourier transform of a constant function, 1, you get 1, so multiply by delta, you get, add 0, you get 1. It's just a characteristic function of the whole group, or the whole of Zn. So f hat of 0 equals 0, and f hat of r equals a hat of r for all r not equal to 0. And that's because the sum of all the rth roots of unity, all the powers of an rth root of unity, will just be 0. So adding this constant function doesn't make any difference to the non-zero Fourier coefficients, and it kills the 0 one, and that's quite useful to us. So let R be such, I better write it, let R be such that a hat r and therefore f hat of r is at least eta. So then eta n, it turns out to be convenient actually here to work with sums, even though normally I work with expectations, and that's because we're going to be splitting up into some arithmetic progressions. So eta n is by definition, is n times f hat of r equals n times the modulus of the sum over all x in Zn fx times omega to the minus rx. Here omega equals e to the 2 pi I over n. I sometimes like to use that notation. Actually, in the notes I didn't use that notation. Equals, but now I'm going to apply the triangle inequality. So this sum here I'm going to split up into the, first perhaps I should say, I forgot to say this, so by lemma 3 we can partition 1 to n into arithmetic progressions P1 up to Pm of size at least eta n over 64 pi to the half, such that the diameter of omega to the r pi, so omega to the r pi is going to be e of theta pi for theta equals r over n, so such that that is less than or equal to eta over 2 for all I. So now we will just take this expression here and apply the triangle inequality. That is less than or equal to the sum I equals 1 to m of the sum over all x in pi fx omega to the minus rx. Let's have a new page. So now I'm going to let, for each I, let xi be some arbitrary element of pi. And so let's continue the, whoops, I can't do this without extending the page. So let, this is going to be less than or equal to, apply the triangle inequality again, sum I equals 1 to m. So the expression I sort of want, for reasons that will become clear, so fx omega to the minus rxi, plus a little correction factor, so, or correction factor is not quite the right word, but I equals 1 to m. I think I'm going to need a new line here. Plus sum I equals 1 to m sum x in pi f of x times omega to the minus rx minus omega to the minus rxi. And this bit here actually equals, because this omega to the minus rxi is actually constant over this progression here and has modulus 1, so that just equals sum I equals 1 to m sum x in pi f of x. So the idea was that this thing is roughly constant, and so this whole expression should be, sorry, this expression here should be roughly just the sum of the f of x's. And that's what we're proving now carefully. So we're saying that it's equal to this thing plus an error term. And what's the error term? Well, we know that this is at most eta over 2 because we fixed it so that the diameter of this function omega to the rx is at most eta over 2 on each progression pi. So that has size at most eta over 2. F of x has size at most 1. And then, so we will get just at most here eta over 2 times the size of this progression, and then we add up over all the sizes of the progressions, we get n, so plus eta n over 2. And let's just go back and remind ourselves what the left-hand side of this was. We had an eta n here, so eta n is now less than or equal to this thing plus eta n over 2, and so rearranging, we get that sum I equals 1 to m sum x in pi f of x is greater than or equal to eta n over 2. Now unfortunately that's not quite good enough for us because we want this thing to be greater than 0. So an averaging argument tells us that at least one of these things here will be reasonably large. Perhaps I'll just comment that this is eta over 2 times the sum over all I times the size of pi. So we get by averaging that at least one of these is bigger than eta over 2 times the corresponding pi. But that's in modulus. In order to deal with that, there are different ways of arguing, but a nice way of arguing is to say the following, and this is why we passed to f instead of a. So so this is just a little slick trick, I would call it. So sum I equals 1 to m, sum over all x in pi f of x equals 0. So now if we add these two expressions together, or these two inequalities, or this one's equality, together and use averaging, there exists an I such that sigma x in pi f of x modulus plus sigma x in pi without the modulus is greater than or equal to eta over 2 times the size of pi. And I think I've stated the theorem slightly, not quite correctly, the lemma. But let's just quickly finish. So if this is negative, then it exactly cancels this out, and it can't be greater than or equal to eta over 2 times pi, so it must be positive. So that implies that 2 times this is greater than it, so that implies that sigma x in pi f of x is greater than or equal to eta over 4 times pi. And it's greater, it's without a modulus sign, because as I say, if this would happen to be negative, we'd get 0 on the left-hand side. That was the slick trick. But what is f of x? It is delta plus a of x. And if I sum a of x inside pi, I'm just getting the size of a intersect pi. So that implies that a intersect pi is greater than or equal to delta times pi plus eta over 4 times pi. And I think in the statement I accidentally wrote eta over 2, so let me go back and change that, because it should have been eta over 4. I better check in the notes whether I got that right, but I think I probably did. No, maybe that's overconfident. Okay, so that's proved that lemma. And I would say that the proof of Roth's theorem is now all over bar the shouting, because we have now established that if you only have small Fourier coefficients, you get progressions of length 3. And if you have a single large Fourier coefficient, then you can find a fairly long subprogression inside which the density has gone up by a significant amount. And we can then repeat the argument. And we can't repeat it too many times, because otherwise this density would slip up above 1 and we have a contradiction. So therefore, at some point, we must be in the first case where there are only small Fourier coefficients, and we're guaranteed a progression of length 3. So that's the idea. But let me now spell it out in a bit more detail and show you a few back-of-envelope calculations. So proof of Roth's theorem. And so just to set up again, we've got A sitting inside 1 to n. Slightly hesitating between 1 to n and 0 to n minus 1, but we'll go for 1 to n. And the size is at least delta n. Now, first step, we want n to be odd, but n might not be odd, so what can we do in that case? If n is even, right, actually let's call it n naught. Right, n naught equals something like L naught plus, maybe I can even call this set A naught as well, and this density here delta naught, because this is just to emphasize that we're doing an iteration. So L naught plus M naught, where L naught is just L naught and M naught are odd, and at least, well, if n were equal to 4, then that seems like the worst case. Then one of them would be 1 and the other one would be 3. So we can get them at least to be n naught over 4. And of course, if n naught is large, we can get them to approximately n naught over 2, but let's just be a bit stupidly careful and call it n naught over 4. And now I will have a sort of temporary variable, so to speak. So either a naught intersect L naught is greater than or equal to delta naught. Sorry, by L naught I mean 1 up to L naught is greater than or equal to delta naught times the size of L naught, or a naught intersect L naught plus 1 up to L naught plus m naught, which I'll call n naught since it is n naught, is greater than or equal to delta naught m naught. I don't know why I put those modulus signs there. So in the first case, let A equal a naught intersect 1 up to L naught, and let n equal L naught. And now n is odd, and n is my, as I say, my temporary variable. In the second case, let n equal m naught, and a can be a naught minus L naught intersect 1 up to m naught. So what have I done there? I've just taken the second part of the set where a naught is big and then just shifted everything back, so that instead of that going from L naught plus 1 up to n naught, it goes from 1 to m naught. So either way, I've got a nice dense subset of 1 to n. Okay, that was just a sort of boring preliminary, but if you want to feel better about it, I used to think, before I noticed that I could get away with n being odd, that it really was useful for n to be prime. And then it was much more tedious. You had to use the prime number theorem and whatnot to split it up into some, to get a prime part. You couldn't split it up into 2 primes because, yeah, never mind. There was a much more tedious argument, but this one's nice and simple. Okay, so now we have a couple of cases, but actually before I do that, we're going to let B equal A intersect n over 3 up to 2n over 3, and C equals C actually. Now we have 2 cases. So this set, which is equal to B and C, has size less than. So if everything were nicely sort of fairly distributed amongst the first third of the numbers from 1 to n, the middle third and the last third, we'd have delta n over 3 elements here, but actually I'm saying it's got delta n over 5. Then either A intersect 1 up to n over 3 is greater than or equal to 2 delta n over 5, or A intersect 2n over 3 n has size at least 2 delta n over 5. So there are some annoying integer parts to worry about, but actually we're going to assume that n is really quite large later on, so assuming that n is greater than or equal to 1,000 or something, which I think we'll probably have. Yeah, I think we definitely have that later on. this gives us a progression P, either this interval here or this interval here, so of size greater than or equal to, say, n over 4, so I'm being really generous, I didn't need to be greater than or equal to 1,000 for that, such that A intersect P has density at least, so 2 delta over 5 divided by a third makes 6 delta over 5, and because it's not quite exact, let's say 11 delta over 10 or something like that. And in that case I'm very happy because, times the size of P. I'm extremely happy about that because that's exactly what we're trying to do. We're trying to pass down to a subprogression inside which A has bigger density. And in fact, getting a subprogression of linear size, n over 4, is succeeding beyond our wildest dreams. So in this case, it really isn't important to be very careful about the numbers, because if you've got anything even remotely good like this, that's absolutely fantastic. And we can pass happily to case 2. So case 2 is, of course, the opposite. So A, which I won't call it this anymore because it's the same as B and C have density greater than or equal to delta n over 5. So that's exactly the same as saying that this set has size, greater than or equal to delta over 5. So what are we going to do here? So now we apply lemma 1. We find that either A cross B cross C, and hence A, because B and C are subsets of A, contains a non-trivial arithmetic progression of length 3, or there exists R not equal to 0 such that A hat of R is greater than or equal to delta squared. I believe it was delta squared over 20, but I think I ought just to quickly check what I obtained. Okay, so it's alpha beta to the half gamma to the half over 2, so I didn't need to go back as far as that to check. I only needed to go back as far as this. So I want to apply this result with our alpha, beta, and gamma. Beta equals gamma equals delta over 5. So alpha, actually it gives over 10. So alpha is a delta, and beta to the half, gamma to the half gives us a delta over 5, and then we divide by 2, so we get delta squared over 10. So in the second case, so in the first case, bingo, we've finished. In the second case, by lemma where's it gone? By lemma 3, we can obtain a bound like this with eta equals delta squared over 10. So we're going to get delta squared n over 640 pi to the half. So let's go back again. So by lemma 3, there exists a progression P of size at least delta squared n over 640 pi to the half. Obviously I can take the delta squared out and put it as a delta if I want to, but it's not very important. And A intersect P has size at least delta plus delta squared over 20. 40, because it was eta over 4. delta squared over 40 times the size of p. So now we're happy in this case as well, because we've managed to find a progression that's reasonably long inside which the density has gone up. So now let's, so again, I've already said that the proof is basically over. Now it's even more basically over. What remains is to do a little calculation to see how many iterations we can possibly do before this density goes beyond 1, and also how large the starting n0 has to be. Oh, by the way, in the second case, I haven't specified this very carefully, but in the second case, or in either case, so if we have p such that A intersect P is greater than or equal to delta plus some, let's choose a new letter, zeta times P, then we can find a linear map phi that takes P to the set 1, 2 up to size of P, and phi of A does not contain, because of a linear map like that is going to be a Freiman homomorphism, does not contain a 3AP. So we can set A1 equals phi of A, N1 equals the size of P. And now we're in a position to iterate, and delta 1 equals delta plus zeta, which in this case is going to be delta plus delta squared over 40. Perhaps I'll make zeta delta squared over 40 again. And that was delta naught. I suppose I could have said that. So that's how the iteration works. So let's just see again how many times we can iterate before we can iterate the function delta goes to delta plus delta squared over 40 before it goes above 1. So observe that if we iterate 40 over delta times, or if we start at delta and iterate 40 over delta times the function delta goes to delta plus delta squared over 40, we've added at least delta squared over 40, in fact a little bit more as you go on, but at least delta squared over 40 times, 40 over delta times I mean, and delta squared over 40 times 40 over delta is delta, and so we got up to 2 delta. So then the density goes up to at least 2 delta. And then, of course, if we iterate 40 over 2 delta times, it'll go up to at least 4 delta, and so on. So the total number of iterations is at most, before you get a contradiction, or before you are forced into the first case where there's a small Fourier coefficient, there are no large Fourier coefficients, is at most 40 over delta times 1 plus a half plus a quarter plus and so on equals 80 over delta. By the way, by that and so on, I'm not suggesting you iterate infinitely much. I'm just saying this is an upper bound for the number of iterations. Now, let's think a little bit about, let's just remind ourselves what happened to the size of the, I've lost it here, wait, what happened to the size of the progression. So n1, that was an n0 over 4 at least, so we get that nk plus 1 is greater than or equal to, so this n becomes an n over 4, so that 640 becomes a 2560. So delta squared nk over 2560 pi to the half, which is at least nk to the third. So that's a really crude thing to say because it's actually just a constant times nk to the half, but we can afford to be crude here, you'll see. So it's at least nk to the 1/3 if so nk to the 1/6 is greater than or equal to 2560 pi over delta squared to the half. So we need k is greater, nk is greater than or equal to 2560 pi cubed times delta to the -6. So that's some biggish number, but I don't really care. And what else do we need? Well, we also needed that for the arguments to work. If you remember, there was that bound n greater than or equal to 2 over alpha beta gamma, and alpha beta gamma was so beta and gamma were delta over 5, so we get something like 50 over delta cubed. But that 50 over delta cubed is completely swamped by this bound here. So the iterations can continue, provided we always have that nk is at least that amount. So I'm going to cross this out again, because that bound we also need, but we definitely got it if we've got this one. Now, how big is nk going to be after 80 over delta iterations? So enough, if the original n, which for safety's sake I'll call n naught, what will that go down to after 80 over delta iterations? It'll be raised to the power 1/3 raised to the power 80 over delta, and we'd like that to be greater than or equal to 2560 pi cubed times delta to the -6. And here comes, all we've got to do is just some sort of, as I say, back of envelope calculation, and what we'll see is that what I have on the right hand side here really matters hardly at all, because in order to get a handle on delta we're going to have to take logs twice, and that's just going to kill everything here. So let's do that. So taking logs once, we get 1/3 to the 80 over delta log of n naught is greater than or equal to, oh, this delta is actually delta naught as well. Okay, in fact, because of that, I think I'll just say from now on, when I say n, I mean the original n naught. And when I say delta, I mean the original delta naught. So that should be at least 3 log 2560 pi. Let's get a bound for that. So 2560 times 3 is at most 10,000. Let's put that instead. Plus 6 log 1 over delta. And so it is also enough if 80 over delta, actually that log of 1/3 is going to be negative, so I'm going to take it over to the other side. So log n is greater than or equal to 80 over delta log 3 plus log, the rather disgusting expression, 3 log 10,000 plus 6 log 1 over delta. And we can be, actually that's an if and only if, but if I want to, I can turn it into just an if by replacing that, just to simplify things, by log 3 plus log 10,000 plus log of 6 plus log 1 over delta. Now, the thing I'm going to do at this point, so that's replacing this bit here. What I'm going to do here is just say enough, also that is implied by, so it is enough if log n is greater than, let's say, 200 over delta. So I just added a whole bunch of stuff to that, and 1 over delta is a lot bigger than log 1 over delta, and 200 is a lot bigger than log 6 or log 10,000 or log 3. So I've really just been, well, even 100, I've really been very, very generous here, and I can't be bothered to try to be less generous. So it's enough if that's the case. So we can say that in two ways. It's enough if delta is greater than or equal to 200 over log n. So that is a density that suffices to guarantee an arithmetic progression of length 3. Or we can say it the other way around. We can say n has to be at least e to the 200 over delta. So we get a sort of doubly exponential bound in 1 over delta. You might ask, is that the best bound you can do? And that's been a question that's been very, very much studied over a number of years. And I'm not going to give you a big history of that, but I will say that the most recent result in this direction was a very exciting result by Thomas Bloom and Olof Sisask, who obtained a bound that said that it was enough if the density is at least some constant over log n to the 1 plus some other little constant, where that's a positive constant. And the reason that was exciting was that that gave a purely combinatorial proof that the primes contain infinitely many arithmetic progressions of length 3, because now we've gone below the density of the primes. That result has been known since Vinogradov and van der Korput in the early 20th century, and more is known as the green tau theorem that tells us that that's actually true for progressions of length, of all lengths, but not with a bound like this. Green and tau used facts about the prime numbers that went beyond just their density. There's a famous conjecture of Erdős which says that if you have a set of integers such that their reciprocals diverge, then A contains arbitrarily long arithmetic progressions. And that's essentially equivalent to saying that for any particular k, the density you need is lower than 1 over log n. That turns out, if you think about it, that's roughly what this is saying. And so another exciting aspect of what Bloom and Sisask did was that they, for the first time, they gave a proof of this, at least in the case of progressions of length 3, even that was not known. Okay, so I will stop there, but what we're going to build up to next is how to start thinking about arithmetic progressions of length greater than 3. There are various reasons that this argument doesn't work straightforwardly, but it turns out that there are things that can be done. And that's the end for now.